Everybody, time for another installation of hard challenge problems in Physics 124. This is the conservation of angular momentum collisions problem for, I guess it's homework problem 7 on week 9. And what's happening here is we throw a ball of putty at this rod suspended from the ceiling. It's got a little pivot point up here, and it's going to swing back and recoil. And the situation is set up so that we have two stages to this problem. I'm going to sort of divide my work here in two. Over here, I'm going to have angular momentum conserved. And that's set up because while the collision is happening before and after, there are no torques on the system. The gravity is sort of straight up and down, it's not moving at all, and we just sort of splat together. And much like an inelastic linear collision, we get an inelastic angular collision. Over here, after they splat together, there are no non-conservative forces acting on the system. So what we end up with is a conservation of energy problem. And that's something we can solve using the methods we've developed previously. But the conservation of angular momentum is new. And so that has a final angular momentum equal to an initial angular momentum, where this is showing the initial angular momentum of the bar at rest and the particle coming in and getting ready to splat. Now we know that the initial angular momentum is going to have some form that is going to be the mass times the speed times the perpendicular distance with respect to the observer or the origin. And then afterwards, we're going to have something that is rotating with a moment of inertia around a pivot, around a point. And because we have a pivot point up here, it kind of makes the most sense to define my angular momentum with respect to this point up here, where this vector here is going to be the r in my angular momentum of a particle, and therefore r perpendicular is going to be that part right there, so that's r perp. And you should be able to see that r perp, because it's coming in right here at L, is going at L over 2, is just going to be L over 2. So then this is going to be the mass times the speed times L over 2. And so that's the angular momentum of the particle coming in here. That's r perp there. The moment of inertia of this system after the collision, I don't know what the angular speed is, that's what we care about, is going to be the moment of inertia of this bar, and so that's 1/3 m L squared. But then there's also a moment of inertia from this blob of putty sticking to the bar over here. So it sits right here, bloop, 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 bloop. And so I get a point here that is m L over 2. And this distance from the origin, or that axle, is L over 2 squared. So this is my moment of inertia, and from that I can actually figure out what my angular speed of this whole apparatus is after the collision. So that's pretty cool. So I can go ahead and say that omega is just going to be mv L over 2 times the moment of inertia, or I'm going to just bank this for later, save me some writing. So that's I. Okay, now I come over to the conservation of energy, and I'm going to say that there are two parts of the conservation of energy. There's the after, when it swings up here, and it comes to rest. So it swings up here, and it's going to swing up by some height difference, h. I'm going to call that h final at the top, and it's h initial. And I'm marking this from the center of mass of the system because that's where the conservation of energy applies. So that's kind of the point I went over in lecture today is that we treat our energies with respect to the center of mass, and this has been carefully rigged so that the center of mass is easy to identify at a distance of L over 2. So that gives me that my final state is going to be that the center of mass has risen to a point H final, and then I'm going to have 0 kinetic energy. So K final, that's going to be 0. My center of mass initially is going to be mgh initial, and then that is going to be added to that is going to be the kinetic energy of rotation. And so that is just that mgh final is mgh initial plus the moment of inertia, or it's 1/2 times the moment of inertia, which I have over here, times that initial angular speed when it starts swinging up. And given this scenario, we want to ultimately calculate what this angle is right here. That's what we're going for in this whole problem. So this gives me my full and complete setup. So when we're all done, we know that mgh final, this distance here, is going to be swung out at some angle, and it's going to have a height that is going to be measured down from the top. It's going to be L, it's going to be, let's see here, mg times h final minus h initial is equal to 1/2 I, and we're back. 1/2 I omega squared. Now we've done this calculation before. That's this distance right here for something swinging out, and we know that that is mg times L over 2 times 1 minus cos theta. And that's just, we've seen this algebra before to figure out that little difference right there. And that is equal to 1/2 I, and I can come over here and put in my value for omega, which gives me m squared v squared L squared over 4I squared. And I'll go ahead and cancel off that with that moment of inertia. And I end up with mg L over 2 times 1 minus cos theta is equal to m squared v squared L squared over 8I. I've got my I over here. I've got a bunch of mg's and l's, and I've got what I care about, the cosine of the angle. At this point, it's just algebra. The physics is done, and I hope you can execute it through and calculate the actual angle of deflection. So good luck with that and the rest of your assignment, and have a great week.